Hello everyone, my name is Bashram. Today I'm going to talk to you about our work entitled Application of Fuzzy Logic for Collision Avoidance of Mobile Robots in Dynamic Indoor Environments. Now I'm going to have a brief talk about introduction that includes motivation and problem statement. And I'm going to discuss proposed scenario, solution overview, as well as the simulation result of mobile robot path planning and motion control. Finally, the conclusion that involves the main points of this work and the scope of the future work that can be done on this study. Mobile robots are increasingly used in the last years in many types of applications, and according to the statistics of International Federation of Robotics that estimate robot installation will increase by 12% on average per year. So nevertheless, some applications of mobile robots are remotely controlled or not fully autonomous. The most important demanding and functionalities for mobile robots are to plan its own motion with different optimization goals, interact with other robots, to have an automatic adaptation and react to the surrounding area. Therefore, the key for the future robotic system development depends heavily on the path planning and motion controlling system in use. And that's why we started the research on the intelligent motion planning algorithm-based control. Problem statement is multiple mobile robots workspace with many static and dynamic obstacles in different shapes and locations. The mission of each robot is to plan its own optimal motion from start point to the target point. So the first question to be answered, which path to take in terms of optimality? As can be seen, although path A is the shortest one, it has the lowest safety performance. Even though the best safety performance is in path B, its length and smoothness are not the best. On the other hand, the best smoothness performance is at path C with minimum number of line segments, even though it is the longest path. And path D has minimum time smooth curve. Nevertheless, it has the low safety performance. So the second question to be answered, how to generate optimal path as trade-off among all of these objectives, as can be seen in the dotted path. And the third question to be answered, how to coordinate with other robots and avoid the collision with them and unknown dynamic obstacles. To solve all these problems, we need efficient motion planning algorithm. Multi-objective optimization. The feasible path structure contains a set of points from start point to the target point. The fitness function in our proposed scenario is weighted summation of multiple objectives in terms of length, smoothness, safety, and time. So F1 is the total length of the path, which is computed by gradient distance. F2 is the path smoothness, which means total angles of all path line segments and the number of line segments in the path. F3 is path safety, which means the sum of shortest path distance between each path point and obstacle. F4 is total time for robot motion from start to the target point. So by minimizing the overall fitness function regarding the assigned weight of each criterion, a suitable optimal path will be obtained. Case study. The kinematics model of the robot case study that has a differential drive system is used. This table shows value of model parameters for the mobile robot that are used for trajectory generating. In the first part of the study, a new proposal for finding optimal path by mobile robots in a static environment is introduced, wherein path planner is designed on this basis that included a modified genetic algorithm using a star algorithm. And in the second part of the study, the fuzzy logic control has been proposed and integrated with the selected algorithm for multiple objective optimized path planning individually and collision avoidance between each robot and other obstacles. So in this scenario, each robot is considered as a dynamic obstacle by another robot. So the second part of the work was designed as a motion controller to avoid such collision. And in this part, fuzzy inference system was designed to safely avoid the collision by slowing down the low prioritized mobile robot. So the proposed fuzzy logic controller is based on the exact location of robots to be controlled, and one of the robots will be considered as a higher priority than other robot. So the design controller has two inputs, namely the planned velocity of controlled robot and the distance between robots, and one output named velocity or controlled velocity. For the planned and output velocity, 9 membership functions have been used. For input distance, 2 membership functions have been presented, where each function has a particle description. And the inputs domain of the system are related to the output domain via a set of rules as can be seen in this table, and the surface viewer between input and output. The output is calculated by the most common defuzzification method, which is called the center of gravity method. However, the previous design doesn't take into consideration any of a non-dynamic and static obstacle environment. So the scope of the work increased to avoid also a non-dynamic obstacle with a small modification by adding an input on board the obstacle detector to control the velocity of mobile robots and avoid collision. Thus to recognize between non-dynamic or static unknown obstacle, so a probabilistic roadmap is required to inform the mobile robot about its free or occupied space. Result video shows the simulation of two robots with a non-dynamic obstacle. It can be observed. The first robot slows down its planned velocity firstly from second robot, and secondly from unknown obstacle to avoid the collision risk. However, robot 2 slows down its planned velocity from unknown obstacle, as well as it slows it shows the distance between two robots that marked in green and blue before and after control action respectively, as we can see in this figure. And the distance between each robot and unknown obstacle that marked in red, it can be observed at distance don't reach zero, which means there were no collision between robots and unknown obstacle. So robot 2 does not receive any control action as it is prioritized robot between two robots. So the main conclusion and future work of this work, the proposed design has been successfully achieved the desired objective and successfully applied in different scenarios with different number of robotics. And the proposed design can be applied for simple and complicated different environments wherein several dynamic obstacles exist. Thank you very much for your listening and attention.